Go ahead and label the top of your notes, MSC, Middle School Chemistry. And this is going to be Unit 4. It's actually called Heat and Technology, but I want you to be familiar with the term thermodynamics. What a cool word. Okay, what a cool word. Thermodynamics. Okay? No, it's one word. And what it means is the study of heat in motion. Okay, the study of heat and motion. We know how we looked at states of matter and energy flow in and out of solids, liquids, and gases. This is an extension of that, okay? So one of the things that's really cool about this unit is that we're going to be talking about some real-life applications of energy flow. What do I mean by that? We're going to look at how refrigerators work. We're going to do an in-depth diagramming of how a refrigerator actually cools things in your home. We're going to look at how your heating system works, whether it be hot water heat or forced air heat, whether it be geothermal or solar heating. We're going to look at why those different options are really popular in today's society. We're going to look at internal combustion engines and external combustion engines. External combustion engines like things like a steam engine and how that works. Okay, so we're going to be looking at these different real-life examples, but in order to understand them, we have to have a basic understanding of heat. This will lead into discussions on why you go to the beach in the summertime. I love going to the beach in the summertime. The sand is blazing hot, but the water is cool. Same sun, same location. Why is the water cold and the sand, so hot? Okay, so we're going to be looking at all of these wonderful things. Why when I touch a metal, it feels, chilly, but when I touch clothing, cozy, okay? So we're going to be looking at all of these things. Don't give me those phony faces, okay? We are going to be asking questions and answering them. It's going to be a lot of fun, okay? Jaden.
Are we going to, do a lab?
There will be a lot of demos, and there will be at least one lab, yes. Okay? So, and actually some of the demos are even this week. All right, let's get started. The main premise for this whole unit is understanding this idea of temperature in a greater depth than what we've already discussed. And because we're talking about temperature, this is going to lead to an even more important idea, and that is this thing called kinetic energy. Oh, I love kinetic energy. Okay, so let's go ahead and write this down. Kinetic energy. We abbreviate it capital K, capital E. All right? Kinetic energy is really important. You will see it not only in chemistry, but also in physics. The study of energy and how it flows in and out and transfers and changes is exactly the whole idea or premise behind science. Kinetic energy is and can be interpreted in simpler terms. We call these layman's terms, okay? So the word kinetic we use a lot, believe it or not. You've used this word before. Let's take a look at these two words, kinetic and energy. Let's break it down. Oh yeah. Let's break it down into what it really means in simplest form. Okay? Kinetic is got a root at the beginning. How many of you like English? How many of you like English? How many of you like writing or reading? Okay, either one. Okay. One of the things you should understand is that most of the English language is based off from other languages. Greek, Latin, German, Spanish, okay? Basically, all of the European countries had influence on our language, okay? And it kind of developed out of these countries. So one of the things, and of course Pastor Lessing would say, what would be the best language in the whole world? Hebrew, right? Well, that's why our names come from so many different origins. Well, kinetic has this root word at the very beginning, K-I-N-E. Okay? K-I-N-E. And this word we use in things like kinesiology. Kinesiology. If you go into sports medicine, the name for it is kinesiology. It's the study of the motion of the human body. Okay? Like the Gatorade thing. Yep. That lady studied kinesiology. How our joints move, how we move, how our muscles interact with our bones, tendons, things like that. So kinesiology, movement. Then there's the idea in physics called kinematics. K-I-N-E, matics. And that is the study of how everything moves from a physics perspective. Okay, and then there is the idea, and this is kind of from my own field, where we talk about kinesthetic learners. That means people who move by being or learn by being hands-on or touching and moving things. So all of these have what as their theme? Yeah, movement. So I want you to think of kinetic energy, ladies and gentlemen, as movement energy. As movement energy. The study or the looking at the energy of movement. Okay? Now, this, okay, kind of directly relates to what we've talked about with atoms in the states of matter, solids, liquids, and gases. One of the things that we defined is that every atom in the entire universe is always what?
Moving.
Isabella?
It's always moving.
Yes. Okay, so let's write that down. And I've got a phone call. Hola. Yes? Yes, I will. Thank you. Okay. Every atom in the whole universe is in a constant state of motion. Okay? Every atom in the whole universe is in a constant state of motion. And therefore, every atom in the whole universe has what? What kind of energy?
Kinetic.
Has kinetic energy, K-E. Okay? Every atom in the whole universe has kinetic energy. So I'm going to move this over just a little bit, and I'm going to give you kind of a way to think about this. Okay? I'm going to do it on both sides of this statement. All right? If something is moving fast, would we say it has more or less kinetic energy? Jaden?
More.
Oh yeah, man. Okay, so if something is moving fast, we would say that that equals greater kinetic energy. Okay? Let's say, though, that something is moving slower, has slower movement. Then, Savannah, what would you say about its kinetic energy?
It has less.
Oh, yes, it does. It has less kinetic energy. Okay, so we have this going on. We have basically this interpretation of kinetic energy. So if I move really fast around the room, and she flinches really fast, we both exhibited a fair amount of kinetic energy. But if I move slow, then that is less kinetic energy. Okay, less kinetic energy. So everything is moving at varying speeds. Okay, in physics, we analyze it more from a speed or velocity standpoint. How fast it's moving, how slow it's moving, and we can calculate kinetic energy that way. In thermodynamics, we are more concerned with its total energy or its average energy and how that plays into temperature. Yeah.
Couldn't you use like a roller coaster as an example?
Oh, absolutely, we could use a roller coaster. In physics, we analyze roller coasters purely from a kinetic energy standpoint. It's a beautiful thing. My entire kinetic energy test in physics, in a physics class, would be based on a roller coaster. Okay? It's a beautiful example. Yes?
So like when you're saying a car is moving,
Yes?
if a car moving really slow has less velocity, and moving really fast has more velocity.
And so then if it has less velocity, it has less.
Kinetic.
And if it has more velocity, it has more.
Kinetic.
Very good, Parker.
So velocity is it the same thing, or is it like it follows it?
It follows it. It's very similar. They're a little different. Okay? But that is just a great example. As a physics teacher in me, I've got goosebumps right now, literally. I can feel them on my arms. It's a wonderful thing to think about it in terms of velocity. Okay? So this idea of thermodynamics, that we're explaining temperature by looking at kinetic energy. We still haven't defined temperature yet, however. We've just introduced that they're related. Okay? That kinetic energy and temperature have a very significant relationship. Okay? So, we could even say that they're brothers and that you cannot separate them. So let's go ahead and take a little bit more of an in-depth look at defining temperature. Now that we know what kinetic energy is, now that we know that it's movement energy, and that everything in the universe has some of it, we can define temperature. All right? So, I'm going to start a new page here. And at the very top of the page, I'm going to go ahead and put the big word, temperature. Okay, temperature. How does this temperature thing play into what we're doing with kinetic energy? Okay, I'm going to write out the formal definition of temperature. I would please ask that you write it in your notes, word for word. Okay, here we go. Temperature is the measure. Notice that word measure. Okay, we use thermometers to measure. Of the average. I'm going to put a big box around that word and highlight it. It's really important. You could even write it. No, it's right. It's in a box. It's important. It is the measure of the average kinetic energy of the, you know what? I don't think I'm going to be able to fit the word atoms there, so let's move it down. Of the, and you guys are right, atoms / molecules. Okay, like water, for instance, is a molecule. Okay, in a substance or object. All right, this is a very important definition. If you go into high school understanding that definition right there, okay, boy, your teachers will be happy. Very happy. If I was your chemistry teacher and you could tell me this is the definition of temperature, that is the measure of the average kinetic energy of the atoms of molecules in a substance or object, boy, oh golly geez whiz, would I be happy inside. Flowers, blooming, butterflies, absolutely. Well, I don't know about unicorns, but mythical creatures aren't really my specialty, but yeah, maybe unicorns. No. Don't give me the credit. If you learn it, it's on you because you get all the credit for remembering. Okay? I just presented the information to you. All right? So we have this idea. It's the measure of the average kinetic energy of the atoms, molecules in a substance or object. Let's look at an example. I am going to create, and you should create a sun on your paper. Okay, here's where the sun goes. Here comes the sun. Exactly. Very good. So here's the sun. And we're going to go ahead and add some yellow here because it's really important. It's really hard to see on the board, but there it is. There's the sun, ladies and gentlemen. What a wonderful thing it is. And that sun is beating down on a book. Okay, so I'm going to draw a book. And that book is going to be right here. And it has a nice binding. Yeah, I know it is. It's awesome. And in that book are pages. Okay, so there's our book. So it's beating down on the book. We could say it's on the beach. Okay. And so we're going to put a little bit of sand underneath it here. And we're just going to put a little sand. Like so. Okay, like so. Now, if the sun is beating down on this book obviously has a temperature. It's made of atoms. Atoms are always in movement, and movement is kinetic energy, and temperature is the measure of the average kinetic energy of the atoms of molecules in the object. So we know it has temperature. If it didn't, it would not exist. And technically, it exists, and so, because I say it does. And so, it has a temperature. This book has a temperature. So we're going to pretend that this book is made of 3 atoms. I know it's a lot, but we can manage. Okay? So we're going to zoom in on this book, and I'm going to draw all 3 atoms. Okay? And I'm going to draw an atom at the top of the book. I'm going to draw an atom in the middle of the book. And I'm going to draw an atom near the bottom of the book, and you can draw those off to the side if that is easier. Oh, I'm seeing some really nice suns and books here. This is very good. Oh, very beautiful. Yes. We are not burning any books. Okay, temperature is not going to be that extensive. Oh, man. Hey, now. Math books are sacred. All right. Now, I want you to hypothesize for a moment. We are going to measure the kinetic energy of the particles in the top of the book, in the middle of the book, and the bottom of the book. These numbers are going to be arbitrary. It doesn't matter what the number is, but arbitrary means that it doesn't matter how specific we are. It just matters that we get them close to each other. Okay? So what I mean by that is, do you think that the atom at the top of the book is going to have more or less energy than the one in the middle or the bottom? Grace. Why do you think more? From? Oh yeah, the sun is beating down radiation and we're taking it all in, sunbathing, okay? You are absolutely right on, Grace. So that one at the top, let's say it has 100 joules of energy. Well, that's a great question. Joules is the unit for energy. Okay, so we need to make a little note off to the side here. Okay, I'm going to make a little note off to the side. I'm going to spell it for you. Joules, capital J, is the unit for energy. Okay, is the unit for energy. So if I zoom back down in on my book, I know that that atom right there has 100 joules. That's going to have more energy. What about the one in the middle? Is it going to be more or less? Emma?
Less because it's not as close to the sun.
Yeah, it's going to have less. It's not going to be as close to the sun. It's not getting that direct radiation, but it's not going to be totally off. Okay, you want to say 50? We'll do 50. That sounds good. So 50 joules. Okay? What about the one in the bottom? What about the one on the bottom? Now, let's assume that it's been shaded. The sand has been shaded. It's not super hot. Okay, so we have 100 joules, 50 joules. This one's the furthest away. We'll go 25. Sounds good.
That's what I was going to say. No, it isn't.
All right. So we have these 3 atoms with different energies. Yeah.
What if you have it on the side? Like
What on the side? Well, in all reality, okay, I picked 3 because it's easy to do this idea. But in all reality, there are trillions of atoms in here, each with different amounts of energy. Okay, the ones near the top are going to have a lot, the ones in the middle, not so much. Okay, and so it just depends.
But I thought the sand was hot.
Well, but have you ever laid a towel out on sand?
Yeah.
And have you ever felt the sand underneath your towel when you've picked it up? It's not as hot anymore because it's not been directly exposed to that hot sun. Okay? Emma?
What if, okay, so like you have the book standing up, like
Yep.
standing on the same. What if you were to lay the book down? Would all the atoms be the same temperature that are on like?
No, because immediately some of the atoms would start to lose some energy.
I mean, like if it was like, because if the book was like this, there would be like an atom. It would be skinnier, but there would still be like 3 atoms. Would all the atoms on the top, like I mean, like would all the atoms on the top be the same temperature?
Would all the atoms on the top be the same temperature? Yeah, they'd be very, very close, yes. And then if I were to flip it over, these would start to cool down. These would then become the same temperature. The ones in the middle would be, but then the ones around the outside are going to be a little different because they're exposed to the air, whereas the ones in the middle will be even cooler because they're not exposed to much of anything. So you got to think about it is that this object is full of trillions of atoms, Isabella, trillions of them. You can't even count to that in your lifetime. And every one of those atoms has what kind of energy? Has kinetic energy. And so what we're doing when we take the temperature of an object is we have to average that kinetic energy or find the mean, if that makes more sense. So how do we find an average? Does anyone want to walk me through that process? My memory's a little fuzzy. Grace? Yep. Very good. So if we're going to find the average, we add them all up and we divide by the number of numbers, in this case 3. So let's go ahead and make a note of this. Okay, because temperature is average, the first thing we need to do is find the average. Okay, so I'm going to go ahead and make a note here. So the first thing I need to do is find the average kinetic energy. Because this right here is what? What is the average kinetic energy of a substance? Yeah,
Temperature.
it's temperature.
We need to know that.
Yep, you need to know that. So this is a pretty easy problem to find the average, okay? This is not too bad. We can do this. And so we're going to go ahead and we're going to add all 3 measurements.
Are we going to do all this too?
Yeah. So Parker, I think you can handle this. 100 plus 50 plus 75. I'm going to write it out here. 100 joules plus 50 joules plus 75 joules. Oh, no, Mr. Bornheimer. Wow, Mr. Bornheimer. No. 25 joules. Okay? We can handle this. Okay? What is the sum of 100 plus 50 plus 25? No! Hopefully it hasn't stopped recording. No, it hasn't. Funky business. Here we go.
Sorry, YouTube.
All right. So, what is the sum of all 3? Gabby?
175.
Yep. So this equals 175 joules of energy. The third part is then we divide by the number of numbers. In this case, we're going to divide by 3, okay, because that's how many atoms we have. I'm going to make a little note here. It's the number of atoms. Okay, so This is going to be then equal to, and I'm going to zoom out a little bit so you guys can see the bigger picture here. 175 joules divided by 3. Can someone please do that on their calculator? Bo Behrman? You have the answer? Okay, let's see it. 175 divided by 3. Uh-huh. It's going to be really close to that. Yeah, 58 approximately. 58 joules of energy is the average amount of energy. Okay. But, and this is where you have to start to have a little bit of creative license. What I mean by that is, that's not a temperature. So how does that relate to temperature? That's energy. That's not Fahrenheit, Celsius, or what you will see as Kelvin. So this then has to be, and I'm going to go ahead and tell you, has to be decoded. We have to decode it. It's actually, and so as scientists, they created their own code. It's called Fahrenheit, Celsius, and Kelvin. 3 different temperature scales. In the United States, we decode that energy by assigning it a value in Fahrenheit. So objects that have 58 joules have a unique temperature in Fahrenheit that's assigned to them. And in Celsius, we assign them a unique Celsius temperature. And then there's this thing called Kelvin, which most scientists use, and they assign it a unique Kelvin temperature. And so what we do is we line this energy value up with a temperature scale. There are 3 main temperature scales in the world that are used. There are actually more than that, but there are 3 main ones. And so I'm actually going to flip over here real quick to the notes. Here they are. Here are the 3 main temperature scales. This is from not your textbook, okay? But I'm going to print off one of these for you, okay? So here's how this works. Here's Fahrenheit, here's Celsius, here's Kelvin. We've assigned them different numbers. Believe it or not, there's a lot of historical information that goes into this, okay? These were developed at different points in time. We've improved on the system. However, because we are very stuck in our ways, as humans are most of the time, we've kept them around. And so instead of saying, hey, let's everyone use Kelvin because that would be so simple, no, we say, let's use this funky thing called Fahrenheit, which has weird numbers like 212.
I like Fahrenheit.
And then we all go, question mark, what? But we learn it, and we use it in America. Most other countries use Celsius, which, by the way, is way easier. And then Kelvin is the easiest, but it's the newest, and so we don't use it very often except in science. Let me explain them. When we developed temperature scales, Connor Shane, when we developed them, we said, hey, well, we know water is going to boil at 212. So whatever the energy of water boiling was, we assigned it 212. And then we assigned it, where it freezes, an arbitrary value of 32. Believe it or not, we did this. We just said, hey, that looks like a 212, that looks like a 32, and so that's what we assigned them, and then we're somewhere in between for body temperature and room temperature. Okay? Well, that's kind of funny, okay? And there's a lot more that goes into it than that, but basically we picked the scale. Celsius also worked really nicely. 0 for water freezes, 100 for water boils, and everything in between. And then there's Kelvin, okay, which starts at 0 at the bottom. You need to know this. Absolute 0 is 0 Kelvin, and it's the theoretical point at which all of the energy of an object has been removed from it. We've never reached it. We've gotten close. We've gotten really, 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 really close. So, ladies and gentlemen, we have just a few moments. Absolute scale is what a Kelvin temperature called. Absolute scales are scales that start at 0 and only go up. There is no such thing as a negative Kelvin temperature. It starts at 0, absolute 0, and only goes up. Is there negative Celsius? Yeah, there is. Oh, absolutely. You can go on the Weather Channel and it'll give you negative Celsius degree temperatures. Does it get negative degrees outside in the winter in Fahrenheit? Yes, it does. Absolute scales do not have negative numbers. Only Celsius and Fahrenheit do. You should also know that absolute zero, as defined, means that we removed all kinetic energy from an object. This has never been achieved. However, how many of you have ever seen liquid nitrogen? Liquid nitrogen is awesome. Liquid nitrogen is nowhere even close to absolute zero. However, if I were to take this table and dip it in liquid nitrogen, what could I do if I tapped it? It would shatter into a million pieces. I could take a rose, dip it in liquid nitrogen, and if I tapped it on the counter, it would shatter into a million pieces. Just tap it.
Like this.
Yep. I could take a rubber ball, dip it in liquid nitrogen, I could tap it, and it would shatter into a million pieces.
Would it like explode or just shatter like glass?
It would shatter like glass. A person would shatter like glass, but we would not do that.